So now we're going to take the sheet that you've got, the worksheet, and try to figure out whether we can use the perpendicular bisector theorem to do these various tasks. So the first question asks, can we use the perpendicular bisector theorem to solve for RS? RS is here. So first of all, we have to ask the question, do we have a perpendicular bisector? Well, this line, which I'll call little a here, this line, little a, is perpendicular to one of the sides of the triangle to TR, and it also bisects TR, because TU is 57, UR is 57, they have equal measures, they are congruent. So this is a perpendicular bisector, and therefore we know that any point on it, such as S, is going to be equidistant from both T and R, which are the endpoints. So therefore we know that SR equals 68. So the answer is yes. We know SR equals 68. Okay, let's go to number 2. Can we solve for HI using the perpendicular bisector theorem? Well, again, we've got to ask ourselves, is this a perpendicular bisector? And we're talking about line JH here. Is that line a perpendicular bisector of segment KI? Well, it's perpendicular, no doubt. But is it a bisector? We're not told whether it's a bisector. We're told this side measures, this segment measures 51. We don't know what that segment measures. Do we have enough to have congruent triangles? Well, we've got a right angle. We don't have any other angles. And we don't have any other sides. So no, in this case, we can't use the perpendicular bisector theorem. We don't know for sure whether HI is equal to KH or not. Let's move on to problem number 3. Can we solve for HI here? Well, first question is, and I'll call this little line B, is little line B a perpendicular bisector of segment HJ? It's perpendicular, and it is also bisecting it. Okay, so we can use the perpendicular bisector theorem, and that means that any point on the perpendicular bisector, such as I, is equidistant from the endpoints H and J. So we know IJ, if it's 76, then HI must be 76 as well. So the answer is yes, we can solve, and we know HI equals 76. Let's move on to problem 4. Can we solve for CF? Okay, so CF is this side over here. We don't know whether or not we can solve for it. First of all, let's ask ourselves, is this a perpendicular bisector? Do we have enough information to know that? Well, we know that it's perpendicular, but we don't know CF, so we don't know if it's a bisector or not. So we can't use the perpendicular bisector theorem here directly. However, let's see if there's any other things we can do that will help us to figure out what the length of CF is. We know we've got congruent sides here. And if we look at triangle FED, that means triangle FED, the big triangle, is isosceles, which means its base angles are congruent. So if we look now, we see we've got clearly 2 right triangles, and we've got an additional angle and side that we know to be congruent. So we actually have angle, angle, side, angle, angle, side. These triangles are congruent, and 59, or CD, corresponds to side CF because CD lies between the right angle and the base angle, and so does CF. They are corresponding sides, and therefore CF is equal to 59. So the answer is no, we can't directly use the perpendicular bisector theorem, but we can conclude that CF is equal to 59. Okay, but we can't directly use, as a first step, the perpendicular bisector theorem. Let's take a look at the next problem, number 5. Can we solve for HI using perpendicular bisector theorem? Well, we know that this line, which I'm going to call little c, or I could call it GI also, same thing, GI, it does bisect segment JH, doesn't it? Because the 2 resulting smaller segments, JG and GH, are congruent, they have equal measure. But we don't know whether it's perpendicular or not. So without knowing anything more, no, we cannot conclude, using the perpendicular bisector theorem, anything about HI. And in fact, we know GI is congruent to itself, so we've got side, 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 but we don't have a third side or an angle anywhere. So we cannot solve for HI. We don't have enough information to be able to. The next two problems ask us to find the indicated value. So 6A asks us to solve for EF. Well, can we use the perpendicular bisector theorem here? Yes, we can, because clearly line FD is bisecting segment GE, because each of the resulting smaller segments are 45 in measure, in length, and it's also perpendicular, so it is a perpendicular bisector. So that means that any point along line FD, including F, is equidistant from the endpoints of the segment that it is the perpendicular bisector for. So F is equidistant from G and E, which means that if FG is 48, then FE also has to be 48. So FE or EF is equal to 48. Going over to B, we're given that DE is congruent to EF, so I'll make a little mark for that. We're told CF is equal to 2, and we need to find out what CD is. Well, can we use directly the perpendicular bisector theorem here? Well, we know it's perpendicular. We know EC, line EC, is perpendicular to segment FD. Okay, we know EC is perpendicular to segment FD, but we don't know if it's a bisector or not, right? In fact, we don't know the size of this segment, so we can't directly use the perpendicular bisector theorem. But we have a side, and because the larger triangle EFD is isosceles, we know that the base angles opposite the congruent sides, which are the base angles D and F, those two angles are going to be congruent as well. And since this other angle here is also a right angle, again, we've got angle, angle, side. And since we've got angle, angle, side, we know that the triangles are congruent, so we could basically make a statement that triangle CDE is congruent to triangle CFE because of angle, angle, side. Do you see another reason that we could have quoted also for why these two triangles are congruent? In this case, we have another reason we could have equally used, which is hypotenuse leg, also because of hypotenuse leg. And that's because we are told that the sides opposite the right angle of these hypotenuses are congruent, and we know that EC is congruent to itself, and that would be one of the legs of each of the right triangles. So we could either use the congruent base angles, right angle, and congruent side to give us angle, angle, side, or directly use hypotenuse leg. So since these two triangles are congruent, CD then is equal to 2 because it is a corresponding part of a congruent triangle which is congruent. So therefore CF equals CD, CF is 2, therefore the measure of CD is also 2.